Okay, hello. I want to welcome everybody to the Geological Society of the Oregon Country, and it is wonderful to see so many faces here tonight. Let me get it to advance. Okay, this, as you might have heard, this program is being recorded and it will appear on our website for future viewing. We've been exploring the Pacific Northwest since 1935, so we're in our 86th year. And this group has had many notable people involved in it. Started by Dr. Edwin Hodge in 1935. John Elliott Allen was president at one time, so was Lon Hancock. You might have heard Lon's name, Hancock, Camp Hancock, and was instrumental in OMSI as well. Our Friday night lectures are held at Kramer Hall at PSU during normal times, and all our lectures are open to the public and free. Okay, during a normal year, we have many activities. So our activities consist of all the things that you see on the screen here. Okay, so we're continuing the evening lectures with Zoom. But we do have field trips. We normally have a holiday party. This meeting is particularly significant tonight because this would have been our March annual banquet. And we have a summer picnic as well, and we maintain a library at Portland State University. So we offer many field trips in the Pacific Northwest, and these are led by experts, and they are, you can see, read the slide there. And I'm going to take a moment and let our field trip director talk about field trips. The lectures are open to the public and free. In order to go on a field trip, you need to be a member, but you can see here membership is very reasonable. Okay, these are the slate of field trips that we have down for sure at this point. And Carol, I'm going to give you a few minutes to talk to the folks here.
Okay, everyone. I'll try to get through this as quickly as possible. This year, especially since we didn't do any field trips last year, we're figuring that we are going to have a lot of members that want to go on a field trip. If you're one of those, raise your hand. All right. So we thought, wow, it's going to be tough to get everyone to get to go on a field trip. So we're trying something new here. We're doing a lottery system, and we're doing that to get everybody that wants to go on a field trip to get on one. So this is how it's going to work. We're having 4 field trips this summer that are major out-of-town field trips, about 4 days each. And there's the list there. The first field trip is first thing we're going to do is a survey, and that's going to come out on March 17th, St. Patrick's Day. That's next Wednesday. And you'll be getting an email about that. And the deal is with being able to fill out the survey, you're going to need to have your wild apricot password. So figure out how to get on wild apricot. You're going to have like a couple of weeks to fill out the survey, and our treasurer and membership coordinator Barb Stroud is going to be around to help anyone that needs help. I can also help, probably not as easily, but that's okay.
You should probably explain what wild apricot is. Not everyone.
That is our membership platform. That is where you pay your money, and it reminds you to pay your money. And we set up our events in wild apricot and all of that stuff. And it's actually seamlessly combined with our website by Mr. Paul there. So you just click on the member login on our website and you put in your password and you're in, okay? Okay, so you're going to fill out this survey, and it's going to ask you which trips you want to go on. And you will have the option of registering one person, yourself, and a second person, which can be another member or a guest. Okay. You are to indicate for each trip if you're not interested, or if you're going to just register one person, or if you're going to register two people. So do that for each trip. We would recommend, if you have a buddy that you'd like to attend a field trip with, and that could be your spouse or can be somebody else in the club, both of you should fill out a survey saying you're going to go and you're going to bring two people. That way you doubled your chances of becoming a lottery winner and getting to go. Okay. So what's going to happen is we're going to pick, we're going to do 4 separate lotteries for the 4 trips. For the first trip, we're going to pick from the pool of people that want to go on that trip. And you will get an email saying that you have gotten a chance to do advanced registration for the trip. And for the first trip, we're going to conduct the lottery on April 1st. And Paul, you might want to put those trips back up there so they can see that that's the Eastern Oregon Volcanics of the Yellowstone plume trip, which I have a little reminder of there behind me. And the advanced registration will be April 5th through the 23rd. We have, for this trip's a little different because we're going to do AWG and GSOC members, and we got kind of 2 registration tracks. But it will, as far as GSOC members go, the registration process will be exactly the same as all the other trips. But anyway, if you get an email saying register for the trip, you will and it'll explain the dates and all of that. You will have that period of time to register for the trip. And then after that period's over, we're going to open the registration up to the entire membership. So if there are any open spots left, anybody can sign up for the trip. Also, if you didn't get chosen for the lottery, but would really still like to go on that trip, sign up during the regular registration after the advance period, and you can get on the waiting list. And, who knows, you might get to go. I think that's all I had. You will be getting emails explaining this as well, so you don't have to memorize it. Okay?
Okay, thank you, Carol. Okay, Carol's put an awful lot of work into all these field trips, so I really appreciate it. Okay, let's see if I can. Okay, so what's new for this year? Okay, we got a new year going on. One thing is we made changes to our bylaws, and those changes to our bylaws allow the president to serve more than 1 year consecutively. So I got to do that this year. We reconfigured our board of directors so that we have a good board. Well, let's see, we reconfigured it so that the burden isn't all on just a few people, and we've kind of distributed the duties more equitably. Okay. And then I want to, just on a personal note, I want to thank you folks for having me, and it's been a privilege being your president for 2 years. It's been an honor and a privilege, so I really thank you for that. And Clay now is our MC, and he is going to conduct a mini ceremony because this would be the turning over of the guard, or passing the baton on to our new president. So I'm going to let Clay take over and talk about the memorabilia, and then we'll proceed on. I'm going to stop sharing, Clay, so you can go.
Hi, this is Clay, your nominal MC for tonight. Ideally, my short segment would be in PowerPoint, but I'm not yet comfortable creating something there, so I'll use Word and QuickTime. Being GSOC president entitles one to possess for 1 year 3 memorabilia: a book, a gavel, and a piece of prospecting equipment. The book is Two Islands by Thomas Condon, Oregon's first state geologist. He wrote this to be a text to get novice scholars interested in geology focusing on Oregon. This particular copy was owned by Charles Rose, a charter member of GSOC. On the flyleaf, Charles wrote, "I used this book as reference while studying geology under Dr. Condon in 1902. On other flyleaves of the book, the other flyleaves of the book has signatures of every GSOC president except for 1957, beginning with Edwin T. Hodge in 1935. What better symbol for a presidency than a gavel? Legend has it that this particular one was carved from wood of a shipwreck on the Oregon coast. I've heard at least 2 versions in our oral history about this, but if somebody would like to do some careful research, it would be an excellent article for a future edition of the GSOC newsletter. The third item is the pickaxe. My grandson Henry hasn't yet participated in any GSOC field trips, but if he does, he'd like to use this. Okay. We assume that the pickaxe was added long after GSOC was founded because the president's name on the engraved plates didn't begin until 1965. And there you see the first few. And it was recently updated with the name of our incoming president, Clark Neuendorf. There's room on the handle for about 15 more names. Okay, now I'm going to shift my screen share briefly here. This might take a little bit of klutzy stuff. Let me try here. Bear with me. Let's see, what do I got to do? I got to share and choose this right here. There we go. And I'll just let the participants speak for themselves.
Present to you the pickaxe of GSOC.
Thank you, Sheila, and I look forward to a very productive year, and a year perhaps that we can meet again in person and not have to really deal with the COVID anymore. And thank you, and I'm privileged and honored to be the next president, 2021.
Congratulations.
Thank you.
Okay, I noticed that there is a couple of raised hands on the screen. So who's managing those?
I think I'm managing the chat. So let me see if, okay. Stone Rhine Cow.
No. No, I see Ruben Bergel and Stephen Russell has had a raised hand.
Oh, I can't see who has raised hands.
Okay.
Yeah, mine was up just, I took mine down. Thank you, Clark.
Okay.
Okay, I'm going to mute myself and let the meeting go on.
Okay. Let's see. Let me share my screen again. Okay, so I'm pleased to welcome Clark as our new president. And he's got a great board. Remember, the president doesn't do that much. The president is only as strong as the board behind him. And I have to say, we have a board of incredibly talented and devoted people. And you guys are what make the group work. So I want to thank you all, and little celebration here for, let's give everybody a clap a hand here. Okay.
Thank you.
Okay, and here's our board. And so, and we're just pleased to have some we have people that have been on the board. We have some new members as well. We're welcoming back Dawn Giuliano, who was our treasurer for many years, and it's great to have her back as a member at large. And then we've also got Scott Burns as a member at large. We're very pleased to have both of them. They're the newest additions, I think. The rest of everybody's been on for a little while. So great going, and we look forward to a really productive new year. Okay, we also have expanded GSOC into the meetup venue. And so Paul, do you want to talk for a moment about meetup?
Sure. Every fourth Saturday at 11 a.m., we have our social hour with breakout rooms, including a welcome breakout room and sometimes a fossil breakout room. Then at noon, we have our grad student, Andrew Dunning, with the geology news. And this week, we're going to have special guests, John Lehman and Dr. Shannon Doolan from the Don't Panic Geocast, which is one of my favorite podcasts. So we're going to have our guests, and we'll have our usual segments. Drop in. You can you can go through the gsoc.org website to get to our meetup page, or if you are a member, you'll get an email with the link. Want to make another quick announcement about Dogami, Sheila, which just very quickly, we can congratulate ourselves as an organization for the work we did working with Dr. Burns and Yume Wong and others to preserve the agency from the governor's chopping block. However, there are still questions of funding, and so the current bill will be amended. You can expect, for those of us who are still concerned about funding the earthquake specialist for that agency, that there will be another push to work on that legislation. And lastly, I'd like to point out that Sheila's being a little bit modest, that in her absence at the last board meeting when her power was out and she couldn't show, we voted to make her a life member. And the reason for that is she has contributed 3 years for her presidency, one before this last 2 terms, and has dealt with a series of crises during that presidency, including the COVID crisis that we had, and has just been an exceptional force for GSOC in connecting us to the community, connecting us to earthquake preparedness, strengthening our relationship to Portland State. And so we all really appreciate her. I think that the strength of the board now is due much to her efforts. So thank you, Sheila, for all of your work. We just love you. We just love you. So that's where I will finish. Thank you.
Okay, thank you. I don't know what to say now. GSOC has a Facebook page, so and I know nothing about Facebook, but I stay away from it as a teacher. I stay away from Facebook, but we do have a Facebook page as well as the meetup. So we're doing a lot of outreach to the community at large. And we do take donations, so we still take donations. Want to just gently remind everybody that that's what keeps the group going. And you can donate online now at gsoc.org, as many of you have. So I want to give a heartfelt thanks to all of you who have kept those donations rolling in. Really appreciate it, folks. And please remain muted during our presentation and ask your questions in the chat. And I've been given the privilege of monitoring the chat questions. So we will, put your chat questions in the chat box, and then we'll address them after Carrie's done speaking. So again, just a reminder that this program is being recorded and will appear on our website. So enjoy the lecture, folks. Okay. I'll stop sharing at this point and change my view. And we're ready to begin with our speaker. So I'm so excited to have our speaker tonight. Carrie Gordon is a wonderful geologist. She earned her degree at Central Washington University when it was Central Washington State College. And I have to say that she turned me on to Nick Zettner before anybody else did about 14 years ago. We knew Nick when, okay? And that's pretty, and we've used his stuff ever since. And of course, he's become a sensation. So Carrie worked for the Forest, she's registered in 2 states. She's a registered geologist in Washington and in Oregon. And she worked for the Forest Service for her career in Central Washington, Northern Arizona, and then even the Oregon Coast Range before moving out to Prineville and being back on the other side of the mountains where she prefers to be. Carrie is also a master naturalist, and I don't know what else to say about her, but you're going to love her presentation. She is just great. So give her a hand and join me in welcoming Carrie.
Thank you, Sheila, and thank you, everyone. Let me go ahead and get my screen share going.
Did I stop mine? I hope, yeah, okay.
Well, this is a real pleasure to be talking with you this evening, because one of the things, and I've shared this with other members of GSOC, is going virtual means that I can participate and I can go to talks all over the United States, and I have been. And this gives me an opportunity to do a presentation from right here in my home here in Central Oregon. Sheila, if my internet connection gets too unstable, you may need to cut my face video, and then that way it'll work a little bit better. We've had
How will I do that?
Yeah.
How will I do that,
gets
Carrie?
a little hesitant.
I think, Carrie, you'd have to do it on your end.
Okay.
Just
Yeah,
to let you know.
Do I need to do it on my end?
Yeah.
Okay, so hopefully it'll come through a little clearer and not quite so hesitant. This evening, we're going to be exploring the Crooked River Caldera. And that's something that's kind of near what we had here in Central Oregon until we had some awesome mappers come and. As a geologist, I'm traveling with friends and family, and I'm looking out the window and I'm seeing something that's totally different from everybody else. I'm looking at the structure, but family and friends are seeing this other beauty. What I'm hoping to see, the same beauty that I do through the stories that these rocks tell. We're going to be talking about the physiographic provinces a little bit, and then we'll dive into the geologic history of our area. But first, geologists, we deal in a totally different time frame from others. And the only math we're going to do this evening is this particular equation. The Empire State Building is 1,250 feet tall. Make that equivalent to 4.5 billion years. And we're only going to talk about the top 15 feet of the Empire State Building, the last 60 million years. So literally, we've had a lot of geologic time that has gone on that we're not really going to talk about. Another way of looking at that geologic time is this timeline that stretches from the inception of the Earth, 4.5 billion years, all the way up here to today. We're really going to be starting right about here at about a little bit about these older rocks. And yeah, they peak through different places, but most of this evening, we're going to be talking about the baby rocks. As an Oregon master naturalist, it's been really fun to learn about the ecoregions here in Oregon. And that goes to explain a lot about what we see when we're traveling. Here in Central Oregon, we're actually at the apex of 4 major ecoregions, but more importantly, we're at the apex of what I consider 4 major physiographic provinces. Blue Mountains, the Columbia Plateau, the High Cascades, and the Basin and Range. Yes, I know those high lava plains are there in the middle, but where I see the big influence is the Basin and Range country moving into our area. What goes on with this is we've got when you drive north out of Central Oregon, you drive up onto the Columbia Plateau, and north it just gets flat, it's pancake layers, it's a totally different geologic underpinning. Physiographic provinces are common rocks and common soils, and they have the common plants and plants and animals that go along with these physiographic provinces. So off to the great. Now you're looking at my tartan instead of at me, and I'm pointing off to the northeast here. So visualize, pointing off to the northeast, we've got the Blue Mountain Physiographic Province, which stretches from Central Oregon all the way to Hell's Canyon. To the southeast is the Basin and Range country. So we're dealing with areas that are getting pulled apart and tugged apart. And then we have the High Cascades with those baby volcanoes off to the west. And all of these physiographic provinces come into play. And for those of you that live up in Washington or you live in Western Oregon, all of our geography has been broken into these physiographic provinces. And that's why when we're traveling, things change. And you wonder, well, why is this vegetation changing as you're coming over the crest of the Cascades and going to Eastern Oregon? It just looks so different. This is the fun part about geology. It's broken up into these cool pieces that you can see as you're traveling. Another piece that we need to talk about before we get into the geologic history is we need to talk a little bit about what has gone on with our area. We actually were oceanfront property for a very long time. Coastline was over here in Idaho. So over the past 150 million years, is when all of these accreted terrains, or this material that's being scraped off the Juan de Fuca plate and pasted onto the North American plate into these big clumps of rock types that basically made up this landscape that we're sitting on. But it got covered up later, and that's what we're going to be talking about. So in order to get this land base, we actually pasted these chunks of material onto the North American plate. And in different little pockets, they pop up and we can see them. If you go down to south of the Ochako Mountains, you can see a little pocket of some Mesozoic rocks, accreted terrains. Or if you're down in southwestern Oregon, you see accreted terrains. But as you see from this cartoon cross-section, a lot of this country has been covered up by these younger volcanic material, all these different rocks. So it makes for an interesting landscape when you go, oh, well, gee, where are all these cool accreted terrains? Well, they're underneath us, and that's okay. This particular image is showing us about the Juan de Fuca plate subducting under the North American plate. And just recently, in fact, yesterday, we were recognizing 10 years ago and the devastation in Japan from a subduction zone earthquake. We're not talking about earthquakes this evening. But what we are talking about is where the subducting plate edge is melting and you end up with these magma pods that rise up and fuel the eruptions along the crest of the Cascades. But we have a different fuel source for some of the other features that we're going to be talking about this evening. So when I moved here to Central Oregon, I was looking at air photos and I was trying to figure out what in the world is going on with these basalt rocks, basically picture gorge basalt, but these basalt rocks that are breaking and fracturing. Well, the fun thing that happened in the last 10 years is a lot of global positioning units have been placed out across the Pacific Northwest and California. And what they are showing is that these accreted terrains are rotating. And as they rotate, they start crumpling up the rocks north of us. So you get into the Yakima fold belt between Yakima and Ellensburg and all these cool little ridges and things that are happening. But right here where we are in Central Oregon, this is where we're kind of in that rotating pivotal role. And some of what I think we're seeing is those brittle basalts getting broken up and fractured. And we see those because of more recent volcanic activity. We've got a lot of volcanic ash that's making those great growing medium for timber. So we're seeing some of this evidence right here in Central Oregon. And that's also part and parcel of what's going on around here. So now we're going to dive into our geologic history. 150 to 60 million years ago, warm tropical seas, we had these wonderful critters like ammonites that were rolling around on the seafloor. And you can actually find some of these south of the Ochiko Mountains in Snow Mountain country, which is just north of Burns. So you can see these Mesozoic rocks, these accreted terrains popping up, and you can find some of these really cool fossils. Well, we lucked out. In 2005 to 2007, Jason McClary and Mark Ferns were tasked with mapping a 7.5 minute quad draped right over Prineville. Now, 7.5 minutes is not a very big piece of real estate. And we were really fortunate that Jason and Mark were able to find the funding to enlarge their map and really get a cool story going. What they found is not one Wildcat Mountain caldera, 40 million year old caldera. They found 2 calderas. Crooked River Caldera, 29.5 million years. This was the part that just was so much fun with them mapping here, is they were finding these features that we had no idea. I moved here in 92 and we had a geology map that showed volcanic terrain all through this area. But it really didn't tell this big story that Mark and Jason found. And that's what we're going to be talking about here. So I know I have a really knowledgeable crowd here this evening. You guys know your volcanoes. So I'll quickly go through this. We all know that cinder cones are steep-sided, short little guys that are very explosive. And most of you have probably traveled to Central Oregon and maybe driven up or hiked up Pilot Butte. Maybe you've been to Lava Butte. These are all cinder cones. And these cinder cones are short and explosive and one-time shots usually. Another type of volcano we have is a shield volcano. So imagine something that's a low rise and it's made out of layers and layers of very runny basalt, and it just gradually mounds up. There's one due south of Prineville, 618 square miles. It's really beautiful and huge. And if some of you are thinking, Is that Newberry? You're right. It's Newberry Volcano. And Newberry does have some other types of volcanoes on the top, but the base is this big, huge shield volcano. Another type of volcano we have here in Central Oregon is a stratovolcano, or it's also called a composite volcano. These are made up of multiple layers of tuff and lahars, volcanic mud flows, and different types of lava flows like andesite and dacite. These are basically layers upon layers, and they're just big, huge features. These three types of volcanoes are ones, when you look across the horizon, they are sitting above the horizon. They're the ones that you can look out and go, that might be a cinder cone. That might be a stratovolcano or a shield volcano. So these are features that are above the surface of the earth. A caldera, on the other hand, is a collapse feature, and it literally is collapsing and falling in. So if you look at this cartoon here, you're looking at this magma that is pushing up against the crust until the whole thing collapses into the interior, like a souffle collapsing. So it's collapsing to the interior, and this material called tuff is rolling out of it. This is not a quiet volcano. This is very explosive. However, on the tail end of that eruption, you end up with these cool little rhyolite intrusions that ooze up along the ring fractures and create domes or mountains around this circular, somewhat circular feature. We have a lot of calderas all over the world, and Jason put together a chart here that shows some of the larger tuff units around both Indonesia and here in the United States. And the size of the bubble indicates the size of the deposit of tuff. So if you look right here, we've got Yellowstone, and Yellowstone's fairly young, 2,600,000. We're talking something that is fairly young and very massive in terms of the volume of material that erupted out of Yellowstone. Move down here a little bit further, and we have the Crooked River, which 450 cubic kilometers. We go a little further down in the graph. Here's Wildcat Mountain. Here's Tower Mountain. Tower Mountain is a 28.5 million year old volcano that is northeast of Prineville. If you have been to Granite or Sumter, if you just turn and look back to the west, you'll see that's where Tower Mountain is. It's between Ukiah and Granite. And then, oh my gosh, look down here in the very bottom, there's Crater Lake and there's Newberry. So we have a whole line of different sizes of calderas, and they're all very explosive. Some of them are extinct, some of them are dormant, and some of them are active, a little more active. So what's this material that's coming running out of these caldera eruptions? It's called tuff. And it contains fragments of bedrock and tephra and volcanic ash. Well, I pulled out the geology map for the area, and I found these pockets of limestone that were mapped right here in Smith Rock State Park, which just, I'm looking at volcanic material and I'm thinking, limestone? Okay. Well, as it turns out, Mark and Jason did indeed find limestone. And what that limestone is telling us is that at depth, where that tuff was ripping up out of the earth and coming up past older rocks, remember those accreted terrains we were talking about? Well, some of them have limestone, and it was picking up chunks of limestone and other types of rocks and encasing them into this tuff. And that's how we ended up with limestone pockets showing up in these walls in Smith Rock State Park. Geologists are kind of funny. We talk about formations like you would a family. A formation has members just like a family does. So that's what this word is all about. The Clarno Formation is a group of different rock types that were deposited during the same time frame, 44 to 39 million years ago. And in this particular map area, this is where that rock is located, the Clarno Formation. Now, when the Clarno Formation was being deposited, had a tropical climate. It was just warm. And if you wanted to go pick coffee beans, we could have done that. We could have gone out the door, picked coffee beans, come back and roasted them. Bananas. We had all sorts of very lush vegetation, a lot of rainfall. And it was during that period where the 40 million year old Wildcat Mountain caldera was erupting. For those of you that have driven from Prineville to John Day, here's Highway 26. This is the end of Ochoco Reservoir. Here we're looking right up Mill Creek, and the Wildcat Mountain caldera takes in this whole upper headwaters of Mill Creek. It literally stretches from Steens Pillar all the way up to Twin Pillars. So it stretches clear through this area. And one of the things one of the reasons I think that Jason and Mark ended up extending their mapping a little bit is I brought them up to a landslide. That's all this yellow stuff is landslide material. I brought them up to a little landslide that had started moving in 2000. And I asked them to tell me a story. Tell me, why did this material start moving? Well, the last story I was expecting was it's because it's the caldera walls collapsing. And that's why we had these big, huge dormant landslides, rotational landslides. It's literally the walls of this 40 million year old caldera that are collapsing in toward the interior. So what a wonderful story. I had no idea. I just said, you guys got to tell me why there's a landslide here. Why did it reactivate? What's going on? Well, Twin Pillars and Forked Butte are dikes, rhyolitic dikes within the Wildcat Mountain caldera. And Twin Pillars it's a fun place to go hiking to because you can walk right into the base. It's the headwaters of Mill Creek, East Fork Mill Creek. As a geologist, we often talk about the geochemistry of rocks. This is kind of a wild, crazy graph here, but what it's showing us is that these tuffs coming out of calderas, all of these tuffs had their own little DNA. They have a chemical signature that is really distinct and unique. And with the Clarno Formation, it's low in niobium, and the John Day Formation tuffs are higher in niobium, which is a rare earth mineral. We also have a distinction between calc-alkaline and tholeiitic. So these tuffs, literally, when the rock looks identical, you could actually take a sample and get the geochemistry of these rocks to figure out, well, did that come from the Crooked River Caldera, or did that come from the Wildcat Mountain Caldera? And it helps with the mapping. So this is part of what Jason and Mark were looking at. This is the John Day Formation extent, 36 to 25 million years ago. And this is when the Crooked River Caldera erupted, we had moved from a really warm tropical climate to this temperate climate, so a lot more like the Willamette Valley. We had sycamores. It was a lot warmer, not the dry semi-arid of today, but it was certainly not quite as wet and tropical as during the Clarno Formation. And I know some of you are very familiar with fossils, but I think one of the most fascinating parts of living here in this part of Central Oregon is we have a terrestrial record of this climate change in plant fossils, but it also shows up in the painted hills. And this is what we're seeing is these red paleosols are evidence of that tropical climate. And then we have these gold, and they're kind of gold beige paleosols that are evidence of the temperate climate. And if you look at this, you can tell that this major climate shift didn't just switch overnight. It vacillated back and forth before it literally landed on a temperate climate. So it wasn't something that happened overnight. The Crooked River Caldera stretches from Ochoco Reservoir all the way up here to Gray Butte, west to Gray Butte and Smith Rock. It stretches from Grizzly Mountain down to Powell Buttes. Here's Prineville Reservoir that we'll be talking about in a minute. And for those of you that are going to come along on the field trip, literally we are going to be touring around through some of these sites where we'll be able to see the evidence of the caldera. Yes, Crooked River Caldera is a super volcano. And we now know from Ray Wells with USGS was mapping in 2014 with the Slits River Volcanics. And so you realize, so this is, Jason and Mark started mapping in 2005. We didn't have the whole question, we didn't have the whole, why is this caldera here answered. And that's the cool part about geology, is we keep gaining information and gathering more and more data. When Jason and Mark were mapping, they were actually proposing something that was a bit of a stretch, because at the time, people were not really open to calderas over on the east side of the Cascades. That was a little unique. What was fueling them? What was going on? And you know, that's why we had to have some sort of a hot spot or a plume. Ray Wells figured out that the Slits River Volcanics were actually the start of a Yellowstone hotspot. And with this whole torquing and twisting of the accreted terrains, we're literally able to place the Yellowstone plume underneath the Crooked River Caldera 29.5 million years ago. So, oh my gosh, now we've got a heat source that's a little more accepted. And just on January 7th, this past January, Vic Camp published in GSA a study that shows the deep mantle plume origin for the Yellowstone hotspot. So we're still continuing to learn more and more about these hotspots. We got this super volcano called the Crooked River Caldera right here in the middle of Central Oregon. So what's the evidence for it? Well, as they were starting to map, they were able to note that down on Prineville Reservoir at the boat launch, you literally see these older tuffs and andesites tipping to the northwest. And the next time you stop Peter Steen Ogden Wayside, walk out on the old highway bridge. There's a number of reasons to walk out there, but the best one is you walk out on that old highway bridge and you look east. And what you see are these older tuffs that are literally tipping to the southeast. And interior to that is all of these thousands of feet, 2,000 to 3,000 feet of Smith Rock tuff. So literally what we're seeing are these rocks that are tipping and showing where this collapse feature is. That was a bit of an aha moment. But there's more. One of the things that geologists that are mapping here in the state or in any of our states, they really require the grace of private landowners to allow them to come on to take a look at the geology. They're not just looking at our public lands, they're literally needing to get onto private land. And in this case, when they got onto a bit of private land due north of Prineville, they found the wall of the caldera. Jason is not really that short. He's over 6 foot tall. So here he is standing on this Eocene andesite, and right across from him is the tuff of Smith Rock. You can't get much more obvious than, whoa, there's the caldera wall. But it's on private land, so it's not something that we can go see. So we're just really fortunate that Mark and Jason were able to get onto that private land and find that obvious wall. Another thing about the caldera is you have these broken fragment. This is on a microscopic level. This is breccia. And one of the things that happens when you're collapsing and breaking all of this rock, it crunches up and it screeches around and it breaks into small fragments. And that's also evidence of a large collapse feature. So they started putting all this evidence together and came up with this Crooked River Caldera. As I said, the geochemistry of these calderas tells them apart. But if you know what tuff looks like, anywhere you travel and see rocks that look like Smith Rock State Park, you look at those walls that people are climbing on. And then for those of you that have been into Leslie Gulch, that's the Mahogany Mountain caldera, 15 million year old caldera. So you're looking at those same types of tuff. So keep that in mind. Once you recognize the tuff, it's kind of indicative of a volcanic environment. If you want to stretch your legs, this is a really good hike in Smith Rock State Park. This is the top of Misery Ridge, and we're looking east across the Crooked River Caldera to Pilot Rock, Pilot Butte, this little Pilot Butte, which is the one east of Prineville, and we're looking over here at Powell Butte. So we're literally looking clear across the caldera, but it doesn't really look like a caldera, does it? It's got this black rock in it. What the heck is that? Well, that's the rest of the story. They also have hydrothermal activity, geysers and steam vents and all sorts of mineralized deposits going on. Well, there were hydrothermal deposits on the north side of the Crooked River Caldera. Where could we go to see comparable deposits today? Yellowstone. So next time you're traveling through Yellowstone, think about what the Wildcat Mountain Caldera and the Crooked River Caldera, Tower Mountain, what did all these calderas have going on around them? They had these geysers and mineral springs and spouts and terraces. It was a happening place. And we can also see evidence of how quickly those soft tufts erode. And that's here at the Grand Canyon of the Yellowstone. These are really young tufts right in here. These are less than 2 million years old. And we're looking at them literally ripping apart and falling apart. And there's waterfalls that are falling over basalt that is pretty rigid, that's right here in the middle of this canyon. So you're dealing with material that is literally falling apart in your hands. It's eroding like crazy. It's a cool canyon. So think about what we must have had here in Central Oregon at one point in time. Jason and Mark were tasked with mapping this area because Prineville was running short of groundwater, among other reasons. And one of the things that geologists do with these fancy colored maps is we draw something called a cross section. And in this case, this cross section stretches from here down to here. And literally we're slicing away down through the Earth's surface to get a sense of what's going on below what we see on the surface. And in this cross section, we finally get an answer for why Prineville is really hard up for groundwater. If you look here, this is the regional groundwater table. It's coming in from the west, from the High Cascades. Thank you, High Cascades, coming across the Crooked River. And at this point where it's crossing the Crooked River, it literally, the river becomes a gaining reach. It's a losing reach prior to that to the east. But at this point, you start seeing all of these springs coming into the Crooked River. Anybody here like Opal Springs water? Opal Springs, thank you very much, Cascades, because they're the water source that is literally popping out of the side of the Deschutes Formation, which is a variety of all different types of volcanic layers coming out of the High Cascades. Well, it bumps up against this ring fracture of the caldera, and you've got 2,000 to 3,000 feet of tuff of Smith rock that's sitting underneath that area that goes on and sits underneath Prineville. So fast forward, Prineville finally, the city managers finally took advantage of the mapping that was done, and they found, with the help with the state groundwater folks and the water resources group, they actually drilled up near the airport and intersected some older water coming through the rocks and along an older path of the Crooked River. And that's the groundwater that we have today for the town of Prineville. So it really did tell the story of what was going on and why the water wells that were being drilled were coming up dry in Prineville. So it's not just pretty rocks. It's not just where are you living and where are the volcanoes. You actually gain information from having geologic mapping done. And groundwater is just one of those pieces of information that you can get. Well, moving on forward, we've got Miocene, 25 to 16 million years ago, semi-arid climate emerging, thick Columbia River basalts were zipping out across the Pacific Northwest. And the Picture Gorge was near the town of Monument and also south of the Ochiko Mountains. And these Columbia River basalts started from the Steens, and they unzipped and rolled out through all of these vents all across Washington and on out to the Oregon coast. And I'm looking forward to traveling with Emily Cahoon this summer, because I'm looking forward to seeing where some of these vents are that are actually south of Monument. I've spent a lot of time looking at the cap rock of the Ochoco Mountains, which is Picture Gorge basalt, but it'll be fun to see where some of these vents, other vents are. So these basalts are fairly massive. And for some of you, you may know this, and it's always fun just to remember this, but if you're a passenger in the car, this is the best part of driving through Picture Gorge, because you get to look at the anatomy of a basalt flow. You get to look at the colonnade and the entablature. And the cool thing about the basalt flow is the molten rock cools slowly into the Earth's surface, and it cools quickly up into the air. And what happens is these itty bitty little columns form, and that's the entablature. And beneath that are big, broad columns that are called a colonnade. Anytime you're driving through the Columbia River Gorge, take a look at those cool Columbia River basalts. You see these entablatures and colonnades. And if I had my camera on, I would show you a picture of one of the best parts, I think, of basalt flows. It's the vesicular basalt. It looks like black Swiss cheese, and it's where all the gas bubbles rise up to the top of the lava flow and make this froth on the top that chills. And wherever you see this black Swiss cheese, this rock that has itty bitty little air bubbles in it, that tells you that you're probably near the top of a basalt flow. It's fun. These black rocks that look really dull are actually telling us fun stories. The last 16 to 3 million years, we've still been very active volcanically. And one of those areas is you can see all of this light green rock here. And when I first moved to Prineville, I drove up onto the viewpoint thinking, oh, I get to see this new town I'm moving to. This is really cool. Look at all of these plateaus right here. That must have been one basalt flow that came out. That's where the old valley floor used to be. It's inverted topography. This is way cool. But there was more to the story, because when Jason and Mark started age dating these basalts, we found out that they're all different ages, and they come from vents that are right near and to the west and to the south of Prineville. So it's actually more to the story, because what this is telling us is the Crooked River has been pretty much in the same place for the last 15 million years. It keeps getting shoved back and forth as these basalt flows come through, and it dams up the river, and eventually the water is so powerful it cuts back down again, but that keeps moving through, and these basalt flows were coming out on these valley floors, and they're protecting some very soft, highly erosive material that's part of the Deschutes Formation. And you also see it at Cove Palisades State Park. These are some of the ash and the ash flow tuffs, 8 to 5 million years old, that have come out of the ancestral cascades. And these sands are so easily eroded. You basically just look at them and they slice and dice. Water can erode these in a heartbeat. And that's one of the fun things about the features that we see at Cove Palisades State Park, is the fact that you've got this resistant basalt that's capping over these soft materials. And when that basalt ends up getting cut, the river cuts through it, it just zips down through all this soft material. And then we have these intracanyon basalt flows that are coming from the ancestral cascades and from Newberry, and they come ripping down the Deschutes Arm and the Crooked River Arm, and they fill it up part way. Think of any flood that you see the floods coming down the Willamette River or down the Sandy, or they're coming down and they're coming, not maybe rolling over the top, but they come part way through the channel, but they fill it up pretty good. And if you're standing on one of those bridges, you're going, whoa, is this going to take the bridge out? Well, think about that in terms of a lava flow coming down through there. This is the basalt of the island, and it's coming from the ancestral Cascades. And this is all that is left with this basalt of the island that literally plugged up the Crooked River and the Deschutes River at one point in time. There's more segments of it upstream from this, but this little island, if you get an opportunity to go up on the island, it's a national natural landmark, which is a national park designation. And if you can get an opportunity to pull Medusa head, here's your volunteer opportunity. The state park, Bureau of Land Management, and the Crooked River National Grassland co-manage this piece of real estate. Now, here's the fun story about this island. You get up there and think about gravity. There are huge tension cracks that run right down through the middle of this island. And you can literally see where the island is, gravity starting to take hold and pull this thing apart. I would also caution anybody who likes to boat to stay away from right at the base of these. Remember those columns that I was talking about? Well, this is basalt and it's columns. And when you get out on the edge of the island, these columns are literally tipping away from the rim up here. So it's not just the tension cracks, it's these columns that are starting to collapse too, to the extent that you've got these big, huge landslides that have also come off the sides of the canyon walls. So it's a very active area. And this basalt of the island is only 1.1 million years old. It's really a young basalt. So now we're moving up to the last 2 million years to 11,000 years. And if you look at this brown polygon here, this is a 400,000-year-old basalt flow from Newberry. 40 miles to the south here. It came ripping down the ancestral Crooked and Deschutes rivers, and it spilled right over the top at O'Neill Junction, down into the Crooked River, raced around the corner, slapped up against the tufts of Smith Rock, on around and on down the drainage. And that's what we're seeing at Smith Rock State Park. That's what you've parked on. When you have visited the park, you are parking on this 400,000, 350 to 400,000 year old basalt flow of Newberry. And that's what has filled up and bumped up against Smith Rock. So it dammed up the river. That's one of those reasons why we have river cobble and lake beds here in the Prineville area. In fact, I live on one of those lake bed terraces. I am not down next to the river. I'm up on an old terrace. When you hike in Smith Rock State Park, you start down over the edge and you get below that basalt. I encourage you to take a look and see if you can't find evidence of river cobble, because there are river cobbles right at the base of that basalt flow. But the Crooked River didn't stop excavating. It kept excavating down to the current elevation today. So if you think about it, that tough image that I showed up front, and most of you have probably been around basalt, who's going to give first is going to be the tuff. The tuff is very weak compared to the basalt. And that's what we're seeing here is we've got this basalt that's rigid and the tuffs have literally been eroded away. So before we leave intra-canyon flows, I encourage you to think about next time you explore from Burns and you're driving down to French Glen, think about that little whoop that you drive up over and take a look at that on an air photo. That literally is an old river channel. And another cool river channel is when you leave Madras and drive north as you're headed up toward Cow Canyon and the turnoff for Antelope, you go up over another little divide. And if you look at the hills on either side, they are also capped by basalt. So this isn't the only place that you can see this type of feature. There's a lot of them scattered around the Pacific Northwest. So have fun looking for these inverted topographies because it tells us where we have something resistant capping something soft. Oh my gosh, now we're finally going to talk about those high cascades off to the west, or actually to the east of those, for those of you that live in the Willamette Valley. These are these pretty ice cream cone peaks, these composite volcanoes and shield volcanoes. Mount Mazama is only 400,000 years old. It really is a baby volcano. Something that I learned here recently is most volcanoes, they only last about 2 million years. They literally erode quickly. So for us to be able to see these pretty volcanoes, they've had a hard life. They've actually been actively eroded by alpine glaciers. They lost 1,000 foot off the top. Boy, talk about taking your elevation down. So these volcanoes have had some kind of hard times with getting worn out, but we still have some really pretty volcanoes here on the crest of the Cascades, and they've bequeathed us with a lot of volcanic material that has covered over our landscape. And the last 12,000 years to present have still been volcanically active. I had an opportunity, and I think most of you did too, to attend a talk earlier this summer about some first-person accounts of experiences with Mount St. Helens eruption. And it literally scared me listening to what some of those people experienced, because I was in Cle Elum, Washington, and we were on the edge of the ash cloud. And this is what it looked like out my kitchen window. It looked like a foggy day, except it was crunchy, crinkly ash with a slight sulfur smell coming out down through the sky. It was eerie, but it wasn't the blackout that we could see going down the ridge just to the south of town. And my parents, 15 miles away on the other side of that ridge, were in complete darkness. So this was pretty mild. This is only 1 cubic kilometer volcanic ash that we experienced. But 7,700 years ago, Mount Mazama erupted, and we ended up with 100 cubic kilometers of volcanic ash. And that fallout stretches from Mazama Crater Lake all the way. You could see evidence all the way through Montana and parts east. And in the Ochako Mountains to this day, there was 1.5 feet of fine volcanic ash that was deposited. And the winds have literally pushed it to the leeward side of the slopes. And if you remember, I talked about that scab stringer, tic-tac-toe look to the Picture Gorge basalts capping the Ochako Mountains. Thank heavens we got that 1.5 feet of volcanic ash that literally jump-started the soil horizon to give us this wonderful growing medium. And that's an advantage of being in a volcanic landscape, because the basalt doesn't really generate, erode, and weather to soils very quickly. But when you jumpstart it with 1.5 feet of fine volcanic ash, it really gets the vegetation going. And we have a lot of plants and animals that really appreciate that type of volcanic material, like the Peck's lily. We've been talking about Oregon's super caldera, which actually it's not the only caldera. There's some calderas that have been mapped, that Jason and Mark mapped, that are down near Eugene. We've got the Tower Mountain, the Mahogany Mountain. This isn't the only super caldera, but it's a pretty good sized caldera. And these will be the stops that we're going to make for our field trip this summer as we're traveling through this area. And I believe we're going to be camping, some folks, I'm going to be in town, but some folks are going to be camping down here at Prineville Reservoir. So you're really going to get to see some really cool rocks down there. Well, we've been talking about Oregon's super caldera, but one of the things that I encourage you to do is explore further with adventures in reading. The Dogami website that we've been talking about keeping alive is a wealth of field trip guides and all sorts of different, sorry for the phone here, all sorts of different types aside Geology of Oregon, which is just amazing. We have Geology of Oregon by Bill Orr, Ancient Oregon with Hiking Oregon's Geology by Ellen Morris Bishop. And for those of you who like a little more in-depth reading, the Upper Deschutes Groundwater Study, which was completed by the Oregon Water Resources Board, really goes in depth into the geology right here in Central Oregon and tells some additional stories about the rocks. And there's other groundwater studies around the state that are well worth taking a look at, because they talk about that geochemistry and the maps and the geology. It's well worth getting your hands on. So I have a quiz for you. What is that big shadow in this picture? Let you think about that a minute. If you said Pilot Butte, you're right. Because most of us, when we're walking up Pilot Butte, we are racing around to get around to see those pretty ice cream cone volcanoes up on the crest of the Cascades. And what we didn't realize is that the majority of that view shed is taken in by the Crooked River, 29.5 million year old Crooked River Caldera. Who knew? For years, I was running up to go see those pretty little volcanoes off to the west and didn't realize that I had a big, huge volcano that I was looking at for most of that hike. So I hope that you'll appreciate all of the physiographic provinces that we live in, and especially here in Central Oregon, being at the apex of 4 physiographic provinces makes for really fascinating travels. We've talked about the geologic history, which has included the Wildcat Mountain, 40 million year old, and the 29.5 million year old Crooked River Caldera. We do live with geology, and our volcanic past has brought us a wonderfully complex environment. And it has been a pleasure talking with you this evening. Thank you very much. And I will go ahead and quit screen share. And open it up for questions.
Maybe we can see your video again, Carrie.
Oh, you bet. What, you don't like my tartan?
Oh, it's beautiful.
And that was one that I wove.
Let me start. Great presentation, Carrie. That was wonderful. I needed you on my last field trip when I took students up to Pilot Butte. Okay. I'm going to ask the questions that came in on the chat, and then we're going to open it up, and anybody else that wants to can ask questions. So The first one I'm seeing that's a question is where in the Crooked River Caldera was the volcanic pipe? Or was there just one pipe or were there several? Where's the vent?
So with my understanding with the Crooked River Caldera, and I'm going to lean on some of our experts that are on this evening, which is Marley Miller and Hal and Pat Pringle, and Clark. So my understanding, though, is that with the Crooked River Caldera, unlike some of the dikes that like Twin Pillars that we know was one of the vent sources for the Wildcat Mountain caldera, the Crooked River Caldera was a big, huge collapse all the way into the interior. And what I neglected to point out, but when I talked about Grizzly Mountain to Powell Butte and Gray Butte to Pilot Rock, those are the exterior rhyolite intrusions that came up around the caldera margin. And that's, so I've never really had them talk about a vent source or vent locations, but I lean on our other experts to correct me if I tend to take the geology and make it broad and general. I didn't realize I was going to have some real experts on the talk this evening.
The question I had, well, you have like an intrusion and it kind of made a big mushroom and then collapsed back down. Was there a central channel or was it one big intrusion and popped back down?
So the understanding is with calderas is they're coming up as a massive magma, but it literally, what's happening is it's destabilizing the crust that's above. And so it's a big, huge collapse that's coming down from all directions. So it's not like a composite cone where you have a main, the central vent. It's a big, huge vent. And that's what makes the whole thing catastrophic, because when the pressure releases, that tuff comes up out of there and literally spills over the edges and over the sides. And that's the part where having that geochemistry can tell you where you have those commingling of different tuffs of different ages.
So the big blob of hot stuff comes up, hits the edge, and goes kapoof, and then collapses down. Okay.
Yeah.
Okay, we also had a question. Somebody asked if there were travertines associated with the John Day Formation anywhere. You want to clarify that since you asked that, Paul?
Well, Carrie mentioned that there was Yellowstone-like activity, including, thermal hot springs. And if there was limestone, could there also be travertines, as there is in Yellowstone?
So in this case, we had this siliceous sinter and SINTER, that silica-rich material that was part of the geysers and the hot springs. And that's the type of material, that one image that I was showing that was off to the north side of the caldera. And I remember looking at some of those rocks when I lived over in that area for a while, and I kept going, man, this is really hard stuff, and you could actually polish it. And that's the cabochon that we were seeing there, and it's silica rich. And so I don't remember seeing anything that talks about the travertines in this area, but we definitely have the siliceous sinter that was going on.
Thank you. The next question is mine too, so I'll ask it, which is, have we progressed any farther in our understanding of the origins of the underlying Clarno Formation? Is it a similar hotspot activity or subduction?
Jason and Mark were pretty quiet about what that vent source was all about. Clark, Marley, what do you guys know?
Well, my understanding is that it's related to sort of the ends time of accretion of siletzia. And so the subducting plate, which jammed up with siletzia, kind of broke off. And we're getting a lot of feedback here because we're looking. Oh, okay. And so that allowed material to come up through basically the broken slab.
So is it kind of like some of that trailing magma that gets pulled along and scraped along and ends up being a...
No, now I'm not hearing it. Oh.
Marley, your mic is on.
Oh, now it's working. Okay. What? So my understanding is that after siletzia accreted, the plate was pretty much stuck, and then the lower part of it broke off, which allowed material to then kind of rise to create these arc-like volcanoes, which included the Clarno and drawing a blank, the volcanoes in Idaho. Anyway, and then the subduction zone then broke farther offshore and started the modern arc. But the Clarno was sort of a precursory to that. That was soon after accretion of siletzia.
All right, thank you.
If that makes any sense at all.
Well, it does. It's all of those little puzzle pieces, throwing all those little pieces together. I just knew it wasn't Yellowstone hotspot.
Okay, and if the speculation now is that siletzia is Yellowstone hotspot, is that still the general view?
Yeah, and that was the information that Ray Wells in 2014 brought that forward, and then Vic Camp took some additional data and with analysis came up with a deep mantle plume origin for the Yellowstone hotspot. So the story is evolving. This is the fun part about geology, that you can go out and go, it's a volcanic rock, it's basalt. But then you go, well, where did that basalt come from? Where's the vent? How did that lahar get here? What's the source? So it's one thing to know the type of rock, but it's getting the rest of the story. And that's some of the fun part about this whole tectonic twisting, is now that explains all of those folded up basalts that you think, oh my gosh, these are rigid rocks, yet they're warped. They're just all of these warps that you drive through between Ellensburg and Yakima. And whoa, okay, now I know why they're crumpled. Okay, cool.
That's great.
Can I add to that a little bit?
Sure.
Please.
Because Vic Camp and Ray Wells just came out with a paper in GSA Today, which I think you can just download off the Geological Society of America's website. And they went into a lot of detail and about a lot of places that they think were intermediary hotspot locations. And ironically, they didn't list, or at least I didn't see it, they didn't list Smith Rock and the Crooked River Caldera in this, although they listed a lot of other places. But Ilya Bindeman at the University of Oregon department, he's done some work on it, and he thinks geochemically that he sees that Smith Rock is an intermediary hotspot location between siletzia and, say, the modern hotspot track.
Cool.
That's really interesting. Our own Dr. Paul Hammond has also talked about the Waverly, which we have here in Portland, which is about 38 million to 40 million, as being part of that hotspot track too. So I look forward to looking at Ray's paper. And Dennis Chamberlain, our board member at large, comments that Nick Zender has a nice session on the Yellowstone hotspots in Siletzia. So he's doing some really interesting work. And Denny has a question too that I'll let Sheila read.
Oh, thanks. I can't find it.
Oh.
I just lost it.
I'll read it. When mapping the perimeter of the caldera, what field marks or features are used to identify the rim?
So that's the detail that I was talking about, finding that piece on private land where you could actually see the wall of the older andesite against the tuff of Smith Rock. So they had a definite physical feature there where they can actually put a mark on the map. And there were places where they had to infer the rim of the caldera. And that's why we're dealing with a 29.5 million year old feature. So we're not looking at something that is really fresh. So that's where the rhyolitic intrusions help mark that perimeter. So you're dealing with Gray Butte and Grizzly and then around to Pilot Butte and then around to Powell Butte. So once they figured out that they had a caldera, it made better sense why there were these rhyolitic intrusions around the edge. So those were other features. And I think the best part for me, the coolest features were what's down at Prineville Reservoir and at visually on the west side of Smith Rock State Park, where you've got these rocks that were flat lying and now are tipped in. And that was a big piece of evidence that you're dealing with something that used to be flat lying and now literally is tipping in toward the center of this caldera.
Okay, and I noticed that Frank Fladkey, Frank, good to see you. Well, even though you don't have your camera on, but Frank also said that he had a comment. Would you like to elaborate on it, Frank? You'd have to unmute yourself. There you are.
Sure. Yeah. I remember when Mark Ferns was working on these things late 90s, early 2000s. And it's sometimes you get really lucky and you find that one particular outcrop that just really kind of clinches the deal. But you really have to piece the picture together from putting together a number of different things, observations that you see in the field. And, when you see a lot of those rhyolites, the extent of those intrusive rhyolites, the rhyolite lavas, well, that tells you something. When you see the distribution of the tuffs, well, that tells you other things. And when occasionally you see ring fractures, well, that tells you some other things. And the field geologist has to put all those things together and then come up with an approximation of where the perimeter of the structure is. That's my 2 cents.
So it's a big puzzle.
It is a puzzle.
Wonderful. Okay, we'll open it up to anybody else who has questions. Just unmute yourself. Okay, I'm seeing some nice comments that you'll be wanting to read, Carrie. And Pat, thanks for putting on the link to that article. I've got it here on my other screen.
Harry, there was one photograph you took on private property that showed, I believe it was the Smith Rock tuff up against a much darker brown, I think it was a basalt. Are the colors that obvious in your photograph, or are they exaggerated?
No, that is Jason's photograph. Remember, this is the private land photograph. So you've got the tuff of Smith Rock smacked up against the edge of that andesite, that Eocene andesite. So yes, it is very distinct, different colors. Andesite, think basalt, think black rock. That's what the andesite is it tends to be, or in our case, it's more of a basaltic andesite, but it's very dark rock. And then you've got this very beige and hey, I've got a camera now. Okay, so here's the cool thing about the tuffs here in the Crooked River Caldera. First time I drove north of town, I looked out and I saw, I don't know if it's going to show, it's pistachio green.
Mhm.
I saw this pistachio green hillside as I'm driving north out Mackay. I thought, what the heck is that? Did somebody put re-green out there? Hey, and it never changed. It stayed the same all the time. It never grew any grass. It was just this green stuff. And then there were other places here in the area where it's bright brick red material. Well, long story short, it's all tough. It's all this beige rock. And oh, Sheila, I want to get one of your cameras. but the thing is there's a cool little clay mineral that alters to the tuff altered to a clay mineral called celadonite, CELADONITE, and that's what makes the pistachio green. And then good old iron oxide makes for the red tuff, and then you've got the beige. And so the beige is the general first color of the tuff, and then it just alters for a lot of different reasons. But these little green spots show up all over the Crooked River Caldera, and it's all tough. It's just altered. But it's one of those fun puzzles that you start looking at rocks and you just, okay, it's still lightweight compared to the basalt, but it's pistachio green? Really? So yeah, that contact is that distinct. The photo was not altered. And I wish I could get on that private land to see that, but that's not going to happen.
Oh, too bad. It should be a national, one of those, national sites. Like Sycamore Point, and the person who owns that land has put up with every geologist in the world tramping over it.
Mm-hmm.
Yeah. Well, maybe someday. Maybe we'll have to go have a talk with him. I noticed Jason is really good with landowners too, because of where he grew up and his origins, and he's really good at talking to folks, go walking out on their property and yeah. So that's good.
Yeah, he does. And he continues to have those same associations with people. And that's
Yeah.
I think the value of how Mark and Jason interacted with people wherever they're mapping is they make those connections and then get those invitations onto the private land. And I think that it adds to the story because of that.
Mm-hmm. Yeah. That was a fantastic photo of the outcrop. Hard to believe. Yeah. Okay. Do we have any other questions, folks? Don't be shy. You have to unmute yourself, though. I will say that. You're all muted. And I don't know if I can unmute them. I don't think I can unmute everybody.
No, I think folks have to do it individually.
Yeah, I think so.
Well, I really appreciate getting invited to speak this evening. Yes, it was a little like, oh my gosh, when I saw Marley and Pat Pringle, I'm like, they should be giving the talk, not me.
In fact, it's so good to see everybody. This is like a GSA conference. This reminds me of the Cordilleran event. And Yeah, so that's great. Wonderful to have all you folks. Really great. Okay, well, I think, let's see, Carol, yeah, let's,
I was just gonna say, I enjoyed seeing a lot of our field trip guides and field trip organizers here tonight, and we'll be in touch. And looking forward to a great